All right, we're recording programming Bitcoin in Rust. We had some technical issues with my upload speed, so we were dropping mad frames on the stream. So we're just going to record this one, and we'll upload it to the... It'll probably take a week to upload, so by the time we stream next week, everybody can watch this one.
We'll have the video there, and you finish mining your Noster vanity and
There you
pub.
go. There you
Quite a
go. I did turn off the mining program while we're recording. My computer's not that beefy to do both. But I've got another laptop sitting over there that is that's mining away.
hashing some in pubs.
I want to get cuz I want to get an ASIC to mine it. And I don't know if that'd be faster or not. I think not, because I think an ASIC's too specific to SHA-256, right? Like I don't know anything about ASIC firmware, but with an NPub and the way I was generating these, I'm having it calculate like 12-word seed phrases, so that way like it's a recoverable NPub. Yeah. Anyway, let's
Mm.
let's work on
Oh,
Bitcoin.
so you're interesting. So you're searching for very specific types of N pubs
Right.
that are like BIP39 compatible.
Right. Yeah. There's an option in there to look for like BIP39 compatible NPubs, or like to
Oh,
calculate it using the BIP39. Which maybe I'll turn that off, and it probably goes a lot faster if it doesn't have to worry about using like the BIP39 words. Um,
oh, interesting. So BIP39 it's not comprehensive. It doesn't cover every possible private key out there.
that's true. Yeah, I don't think it does, or maybe it does. I don't know.
Oh.
No, I guess not. I don't. I have no idea. That's a good question.
Yeah, if it is a subset, yeah, and the both are probably insanely large
Right.
sets of numbers anyway. But
I'm gonna turn it off now you made me think about it. You're probably right. It's probably limiting not only the speed to which I can hash.
like, yeah, the speed that you're actually gonna find
Right.
the input.
Right.
Yeah.
But let's figure out this problem. I mean, all right, so let's see, I added this down here, just generator point test, where it just confirmed that the generator point, because I was trying to think of what we could have, like, messed up, I guess. Like
Mm.
what
So
functions.
what isn't working
So the thing that's
for
not
our
working,
audience?
yeah. So the thing that's not working right now is if we go here and run cargo tests, it's going to run our suite of tests. In this last, or second to last rather, test, so the verify signature, which we were essentially just recreating this verify signature starting on page 66 here, but writing it as a unit test. And in our verify signature, we define the Z, right, which was, we had those
The
definitions.
signature hash.
Yes. And then we had R, which was like the random number. We had S,
Mm-hmm.
which is a signature. We had P and X, which were, those are just points on something, right?
E was the public key.
PX and PY.
Mm.
I don't remember what
Yeah,
those
so
were.
the public key is a point on the curve.
You're right. Yes. Yep. So that's the points for the
So
public
X
key.
and Y are the coordinates.
We defined the prime. Another thing I added in here was I explicitly typed out the prime, so I found like the hexadecimal definition of the prime, and like I
Mm.
created an explicit of that. And then
As opposed to 2 to the power of 256
right,
minus 2 to the
just
power of 32.
yeah, just in case we fat finger that somehow, we didn't. Um,
Mm.
I wasn't quite sure. There wasn't. It didn't seem to be a way to. Oh, you know what? Actually, I know. Okay, I think I know a way we can test out some more things to see if we're getting the right, like where we're going wrong. So we can print out these variables here. The S inverted, or I don't know if that's inverted or not, but it's basically S to the power of
Or
n minus
minus
2.
two.
Yeah, yeah.
N minus two, yeah.
Um,
I think it's inverted, yeah.
but we can print these out and using Python and then compare them to what we get in Rust. Does that make sense? Like if we
Yes.
go into this, I think Jupyter Notebooks. I guess I can't run. I will need to run this another way.
Maybe just pop an extra. Can we run on the same window a Python script? We can, right?
I have the this is the book here.
No, okay.
So this should open up the book and we should be able to run the
Yes,
code
okay.
examples from the book within VS Code. Yeah. So we can go down to verifying signature. Oh, I also had an interesting thought. So creating GitHub on Nostr, GitHub Desktop, like the desktop application, is
Hmm.
um, is open source. So I might just repurpose that to like do Nostr.
Wow,
This
that's so
okay,
cool.
this didn't work. Okay, so we got to install Python 3.
Kernel.
Oh, pip is not installed, of course. Good thing I have good download speeds. I think it's not pip 3 though. It's like Python dash pip 3. Okay, let's see. We gotta. I don't have. So I have Python 3, but I don't have pip installed for it. So I just have to install that really quick. Do. Right? Do I not have pip 3? Oh, there it is. It gives me what I need to install it. See, just type it in the terminal. Linux knows everything. Unable to... What? Unable... What is going on? They're saying I need to run an apt update. I'm also running Linux in Windows, which is weird.
Mm-hmm.
But
Is it
gaming...
like PowerShell or something like that?
No, it's called Windows Subsystem for Linux. They actually embedded the Linux kernel like into Windows.
Nice.
Yeah, it's weird because it's an MSI gaming laptop, so it doesn't like having, like the video card doesn't like having Linux, and there's a number of other just like things that don't work if I have just straight up Linux on it. So
Mm-hmm.
I don't do
Oh
full
yeah,
Linux on it
good.
anymore. Yeah, because all the drivers and stuff get weird. Like I'm sure might be able to figure it out, but yeah, it's just an older laptop.
I see.
I'll wait until I get like a super beefy desktop machine, and then I'll throw Linux on that for development stuff. Or I
Mm-hmm.
won't, or I'll just leave it for gaming, probably. Okay, all right, let's try this now. All right, cool. Now we've got it. But we need to print out some of these. We'll print you as well. We'll print V. Okay. So here's, ooh, how do we print this as hex? That's a good question. All right, Mr. Python, how do we print something as hex in Python?
Oh wow. I don't know. Not something. Yeah, not something I ran into.
All right, let's see.
It's like a 2 hex function or something like that.
Probably. You have to, oh no, that's the question. We want to go to the answer. Oh man. That's
Hexify. Oh, there's
Hexify.
probably a better way.
Let's see if Hexify is available here. No. Yeah. Let's go ask the AI overlords. Okay. There's a hex. There you go. Cool.
That was straightforward.
Very straightforward. So we should be able to do something like this. Yeah, perfect. Cool. All right, now let's run it. There we go. So now we can take these numbers and we need to print these out in Rust now. Oh yeah, you got to give it a format string. So do U and V, and then we can run this test. Let's see what we get output for us. Oh no. Did we?
Did you get int?
We didn't. We didn't print them out as. We didn't print them out as hex.
Ah, so you could just remove hex from the left side.
Yeah.
We're dealing. Yeah, either way.
I just figured
Oh,
hex would just be easier to compare because otherwise these numbers are going to be big.
Mhm.
But we'll see. We'll see how it goes. Okay, so the first number is
yeah.
just completely wrong. So we don't. All right. Well,
Yeah, all of them.
well, if the first one's wrong, then the first S inverted goes into everything else.
Mm-hmm.
So, okay. Well, that was quick. That was quicker. I mean, not quicker than I hoped. That was pretty quick. But let's figure out where we went wrong then.
There's my box. Yeah, that's fine.
I wonder if that mod pow. I wonder if perhaps the mod pow is the issue here.
Mm-hmm.
Oops. Yeah. Because we're supposed to do s to the power of n minus 2 and then modulo it. So maybe we just explicitly, oh, come on. We can explicitly raise, because it's just, well, that's kind of a big number. The modpow function, did we write this? No. It's big. It's the big U int one. See, but that should be right. And this is just this is a built-in number. Maybe let's extract this out and see if this calculation is right. I think it should be. We'll call it prime minus 2. Yeah, and this is sort of what I was trying to do, is just kind of break things down into pieces to slowly suss out like where we went wrong. But we can print out this to figure out. And then if we go back over to here, n minus 2, we can print that out and run it. And run it. So 115. Okay, so that looks right.
We've got a match there.
Yeah, so that's a match. At least it looks like it is. See, that's so hard to tell.
Is it?
I don't know. Yeah, that's what I'm questioning myself. Maybe it's not a match. Let's copy them both out and put them side by side.
Huh.
Yeah, those are different. So those are two different numbers. Okay, so we're getting a little bit closer to where our issue might lie. Yeah, the leading one is correct up until right there. And we get a 3. We get a 3 instead of a 2.
And this is prime minus 2, right?
Yeah. This is prime minus 2.
So that means that the prime is different. Oh, we'll keep on digging.
Yeah, let's. I like what you're thinking there. Let's go to where n is defined. Where is n defined? The constant n. Oh, that's defined in the file, right?
Yeah, and the field element, I think. No, sorry, in the point class.
Oh, it's a really useful thing in VS Code is you can go to this outline here. Point.
Oh, wow.
No, no, no. What? Yeah, where's there it is. N. So this so this is the hex for N. That doesn't look like, that's not the same. Because that's the prime. That's like the prime we were using. Or no, I'm sorry. That's
I
not the
think.
prime. This is the prime right here. N is not the prime. What was N?
Hmm.
Back to our cheat sheet.
Was in the order?
Um.
I was confusing the two the other day, or the other hour, like an hour ago. One is the
Yeah.
prime, the other one is the order for
Right. This is the
the
prime. This one is
curve.
calculated. This is the order. So what do we? So the order minus 2. Yes. Yeah. It's the order minus 2. It's the order of the field minus 2. Because it's for division.
The order of the group, right? Like,
Right.
yeah.
So let's, okay, so this should be what is equal to, let's see here. So this prime is right. It's not the prime. It's the it would be the order minus 2. We definitely, words have meaning. So the order minus 2 is what we get wrong here. Oh, look at
The-
we were doing it wrong. We got it wrong from the get go. Do you see where my cursor's at? What are we
uh-huh.
using to calculate the order minus 2?
The prime.
Yeah. Wow.
Which should be the order though. No,
No,
I
no,
think
it's not.
that's
No. The order is the number of, remember, the order is the number of numbers in the set, right? And the prime is just the prime of it. I don't think for this,
but if
because
you
the
look
generator, you have the generator point, right? So the generator point is going to make the order of it smaller than the prime itself, because we picked a starting like a generator point. Does that make sense?
sort of.
So when we were thinking about fields, like finite fields, we were thinking about the order, and it was the prime, right? When you had like 233 or whatever, or like the order of
Mm-hmm.
17. But then when we got to the point where we're using the elliptic curve stuff, you had to pick a generator point to start from, right? Where you
Mm-hmm.
start from there, and then you multiply. Remember, you multiply it by itself until you get to the
Yes.
point at infinity.
And
And
that's when you define the order of the group.
yes, right. And this is it right here. So generator point has the order of n. So if you're starting with the generator point, multiplying it over and over and over again, n number of times, you get to the point at infinity. So the order of it is n, even though it's using the prime of the other prime. Because we're defining the specific Bitcoin curve, right? So instead of
Mm-hmm.
starting elsewhere, we're starting at the generator point. That's why it's called the generator point, I believe, or at least makes sense why that would be called the generator point.
Hmm.
So if we started at
Big.
0 or a different point that was like the one step
Mm-hmm.
away from 0 or whatever, one step away from the infinity point, I think then the order would be bigger. But because we started at a specific point, the generator point, right, which is which has this X and Y. We started with an X and Y coordinate. So like if you think about it like a number line, right? Like if we have all the numbers in an order, and you over here you have like the infinity point, and you also have the infinity point here, kind of like overlaps. We're actually starting. Here, let me try to do it in code, like not in code, but like in text. So you have like the infinity point, right? And then each one of these dots represents a point along, or not a point, represents an element of the field, and then you have the infinity point. So what we've done is the generator point is like right here or something like that, right? Now, if we're just defining this field from infinity to infinity, the order of that's going to be that prime number, right? Because it includes all elements in this field.
That prime number being
The
n. No, not
256,
n.
no, the 2 to the 256 power minus 2 to 32nd
Minus.
minus 977. So that's the order of the finite field, but we are taking a step further because we're defining a specific curve for elliptic curve cryptography, and we're specifically using this 256K1. We're picking a point, we're picking an element in that field to generate from that generator point, and it's not encompassing like so. And this might not be the best visualization, but it's like we're starting somewhere in this field of elements, well into it, and then we're multiplying it by itself, and it's probably selecting various points throughout the entire field, but it's not selecting all of them because eventually we hit the infinity point at infinity. So it's like the order of the generator point. Let me try to think of a way to phrase this. When you are looking at the order of just the field itself, without the generator point, the prime makes sense that would be the order. But when you're looking at it with the generator point, because of the way the math works out, because you're starting from a point somewhere in the middle, you're not going to include every single element in the entire field, which is why the order is less than the prime by a significant amount. And whatever that delta is, that difference, probably is related to the generator point in some way, shape, or form. Okay. Cool. That makes me feel a lot better. So let's write, all right, so let's, just same way we did a function for this generator point, I'm going to write a function that will give us the order of SCP, whatever. Or we'll just call it N. And Rust isn't going to like that because it's capital. Yeah, we'll just call it N. And we just return this number. Is what I was saying earlier making sense to you or no?
Sort of. I got a little lost, but
So,
let's move on because I think it will start making more sense.
okay. It's because we're defining a specific, maybe the words are in here that I'm lacking to describe it. Because there's a different way of describing the set of numbers that we're working with now. It's called something else. It's like a group. Do you remember that terminology?
hmm Group is like a subset of points
Right.
that when you add them to themselves, they'll eventually get to the infinity point.
Yeah. Oh, no, not that. Cyclical group.
Cyclical group.
Is that what it is? No. Yeah. Okay, yeah. That's the order of the group. Yes.
Mm-hmm.
So we're using a different prime, but N is the order of the group. It's not the So a finite field. Okay. All right. This is all clicking for me. Okay. A finite field has the number of elements that is the same as the order. Right? The order is the number of the elements, but a finite field is going to have like the number of elements is going to be the same as the prime. For
As the prime, right? Not as the order, but as the prime.
right. But this let's see, what is it called? We're getting close. But it's a group. Mathematical groups, I guess. Yeah, I guess it's just called mathematical groups. But this specific group of numbers that we're talking about, it has a defined prime number, which is the SCCP 256K1 prime. But the order of the group, right, meaning the number of elements in it, is n. Because when you start with the generator point, you go n number of multiplications before you reach infinity.
Like self additions.
Right. So
It's like two limited sets, right? One defines the coordinates of each point. That's the prime. The prime defines the coordinates of each point.
Well,
Then you have this limited set of points that defines the number of points you have as a group.
I think
The group that has an order. So it's the order for points.
yeah. Well, I think it's
prime for coordinates for finite fields.
Well, I think the fields are, so there's fields and there's groups. So the field is defined by a prime number, right? And it defines not only how you do the modular arithmetic, but it also defines the order of the field. A mathematical group has a prime number, and then in this case, it has a generator point from which you start generating to get to infinity. And so what we were missing was we were still assuming that we were working with finite fields and not with like a mathematical group, if that makes sense. Yeah, because it's talking about like groups of different sizes, etc. And I could be completely off on this, but it sort of makes sense in my head. Interesting. Yeah.
So now you're using for the S inverted, you're using the order minus 2 as
Yeah.
opposed
Yep.
to prime minus 2.
Yeah.
Okay.
So let's go back and plug this in, and it will probably just magically work. Which would be great.
It would be good. Instead, you're gonna use n.
Right. Yeah.
Every time this n function is called, it returns the order.
The order.
The order. Yeah.
Which in the case of SCC. Okay. So I can say this being very confident. All the other things I said, maybe it's just the way my mind's making sense of it, and it's not the accurate like way of explaining it mathematically. But I can say this is for SCCP 256K1, the order and the prime are two different numbers, and we can see that in the book, right? Like that's uncontroversial because they define the prime with this equation. They're actually two different constant variables. It's p and n, right? Like they're two very, very different numbers.
Mm-hmm.
And we were just using.
Oh, yeah.
Yeah, that's what I'm saying. So those things are very different numbers. Excuse me. And so we were using we were still going off of the understanding that the order is the prime, even though it said it in the book very clearly. It's not.
The order is n.
Mm-hmm.
Nice. Okay.
So I wonder
It's gonna
where
work miraculously.
I wonder. Well, let me see. I wonder where else we were using this. So that's the prime. Okay, cool. Let's see where else we were using this. Just want to make sure we weren't using the number wrong again. No, so it's just in here, just in this verification. Okay, so let's take out these print lines. We can take out this extraneous code here. We can take out U and V, because ideally those should. Actually, let's leave U and V. Actually, and we should leave S inverted as well, because that will. We can compare that to our Python numbers, right? To get a quick gauge on, like, did we do this right? All right, let's. Okay. Let's do it. Uh-oh. Oh. Whoops. Okay. Now we can run it again. Uh-oh, it still failed. Why did it fail? So we still have completely wrong numbers. All right, let's go through and look. So S inverted compared to our Python numbers, which we were printing out down here. We don't need n minus. Maybe we should print out the order -2.
Yeah,
just be
that one.
Right. Yeah. We printed it out for a reason at first. We should have stuck to that reason. All right, let's do it again. All right, grab this number. Find some blank space.
That looks more equal.
It does.
Same
Yeah.
pattern. Right? There we go.
Yeah. All right, cool. All right, that feels good.
Order -2. That is good.
So take that out. But S inverted is still incorrect. We get a weird number. And now we can make sure. Oh.
You still have the prime there, right?
Yep.
Nice. Okay.
I think that's what the problem is. Oh, and look at in these equations too. We're not. So we don't use the. Where do we use the prime at all? Just in the finite fields, I guess, or in the.
Very early.
Wow. Okay. No wonder. Okay. All right. It's all coming together. So we were just never supposed to use that prime in this equation, in this signature verification, because
when you're generating the 256 point,
right.
X and Py are finite fields with the prime as
right, and this is where we
with the prime as a prime. What's the prime? The prime is the field size, right? The size of the field, whatever.
No, the prime is not the order.
No, but for the points themselves.
for the elements of in the
Prime is
points. Yes,
the field elements. Yeah,
and we
yeah. The prime is only used there like very early in the
yeah,
points.
right here. So just for the element.
The field elements. Yeah. Hmm. Then
Okay.
it's all about the order.
So we were
That's good to know. Yeah, that makes sense. Like once you define the points, you only you don't care more about the we don't care more about the primes. It's all about the points themselves.
yes. In the and because the points define the curve, right? So it's all about I think the group is the group of numbers on the curve.
Mm-hmm. Then yeah, you're dealing with points and orders and whatever.
That looks
All right.
Hey, that
That
looks
looks
it passed. It passed. It worked. We're good. It worked.
yeah.
Oh man.
Woo.
Oh. Okay, so we were just all right. That I definitely see how easy that would be to get that confused though. Like, because you go through the whole chapters of like, hey, here's the here's the prime. It's the order. Here's the prime. It's the order. And it's probably just because we're going from Rust to Python and doing some weird translation in there. But
It is. The prime and the order they work very similarly, right? They
yeah,
work as this like an enclosure
well,
that closes up a set.
the prime is relevant to the to the field element itself, where
Hmm.
the this order, the n, this order of the group is relevant to the curve. The curve is made
Yeah.
up of points that are field elements.
Hmm. Points
Weird.
of which the coordinates are field elements. The coordinates
Right.
of these points are field elements.
Right. And those field elements though are within the the constraints of the
Of the
prime.
prime.
So the field elements are within the constraints of the prime, but the curve itself is further constrained to be within this order,
That's wild.
which is base and the order of the curve group, we'll call it the curve group. The order of the curve group is defined by starting with a generator point and then multiply, like doing scalar multiplication on that until you reach infinity.
Hmm.
And then that becomes the order of the curve. Whew.
Same way as if, like in a field element, if you get like number one in a field element, and you add one to itself over and over again, you're eventually gonna reach the prime,
Right.
which then if you mod by prime, you get to zero.
Right.
That's kind of the
Yeah,
infinity
yeah,
point.
yeah. Yeah, yeah. If one's the generator point.
One is the generator point, exactly.
Yeah. Huh.
Hmm. Nice.
Big brains, man. Big brains.
Yeah.
People
Who
like
came up with that?
discovered this. That's what I was just thinking. Like people like figured this out and discovered this by doing crazy mathematics. And I, you know, thank God for that.
Hmm. Yep.
Wow. Okay. All right. We can
Good.
move. We can move on.
I was let me show you this. So let me share. I'll share it on Discord.
Sure. Sure. Sure.
I was like trying to understand the order, like order first, second, third of elements when you're signing a message cryptographically. So yeah, if you open that, it's probably gonna ask you to click on the link or something. Oh, there we go. Yeah, it's weird, but yeah, it's just a Notion page.
Okay.
So if you scroll down to order of events,
Like the yeah.
there you go.
Oh, okay.
So
Yeah,
I
I
was
remember you
like
shared this.
seeing, yeah, what happens at what time, when each variable is relevant.
Interesting.
So
Okay.
I thought, yeah, we could talk about how, like the order of the sequence of things when they happen.
Right.
So the first thing, when someone wants to sign a message, they have to create a private key, which is basically how many times you're multiplying the generator point to arrive then at the public key. So a private key is just an integer that you're multiplying the
Right.
generator point by an X amount of times.
Yeah, I think we wrote I think we put that in our notes. Yeah, it's a single
Mm,
256-bit number.
yes. So when you scalar multiply that generator point by your private key, you arrive at the public key,
Right.
which is what you want to advertise to the world.
Yep.
You don't need to hide your public key. So then, yeah, you have the key pair. So you want to sign a message. What would you do first? You would first generate the Z signature hash for the document you want to sign
Yep.
by running the hash 256 function. Then you would generate a random number k, and based on the random number k, you would find the random point r, which is that third line there on signing.
Right.
You never want to you don't want to review your random number k, because people can find your private key if you review k,
Right.
lowercase k. Or yeah, that's the only case. Okay, whatever. So then when you get the x coordinate of the r point, that's a number you can review. The x coordinate of random point r, that can be reviewed. So for now, we have three numbers that we can review. We have p, which is a point. We have z, which is our signature hash. And we have r, which is the x coordinate of the random point r.
Okay.
And then we just have one last number that we want to review, which is s, which we can calculate with that equation. S equals z plus re.
And this takes
Oh, there
in
it is. Yes.
the numbers that you don't want to reveal, the E and the K.
Yes. Which is interesting. Yeah, you can review the product of that equation, but the result of that equation, but not the
Yeah.
actual numbers in it. So I was testing. So the book says that when you're sharing information to show that you have a private key, you want to share R and S as the signature,
Yep.
Z as the hash of the document, and P as the private key. But I was thinking if R and S were a point in the curve, because they are displayed as this, right? R and S. But they actually aren't. It's just a
No, yeah.
tuple. Yeah.
Yeah. Yeah, they're just
I thought for a second it could be a point as well, but
no, it's
it
just
wasn't the
tuple is
case.
just like it's just very tuple is it's just a very simple data structure. It's just like two things. I mean, I think a point is probably a type of like a specific type of tuple. I don't know.
Yeah, so when you want to show that you are the person that knows that private key, you're providing four elements: R, S, Z, and P.
And the person verifying is going to figure out the big R, the actual random point, because they have to get that X value of it.
Mm-hmm.
Right? because that was part of the signature verification we just did. Was we took, where was it?
Do they know the y of the random point as well?
We took the x. I
Just
mean,
the x, right?
yeah, but we would. I mean, we can get the we could get the y if we wanted it.
Oh, oh yeah, we'll find r that ug plus vp equals r.
Right, yeah. But we just discard y because we're not, like, we don't use that for whatever reason. I wonder why.
Yeah.
I wonder why the x coordinate of r is used instead of the y coordinate.
Actually, is it? I don't know.
Is it in here? I don't know. Rx is the only one we care about. Yeah, it doesn't really say, not in this Notion page.
Yeah.
This is a good Notion page, by the way. I looked at this one after you sent it over.
Yeah.
Just forgot about it because it had been a while.
Mm-hmm.
I should bookmark this.
Yeah. Trying to put the main elements. There's just so many variables, but now, yeah, they're starting to make more sense.
Yeah. Nice.
Okay, yeah. Anyway, yeah, I just wanted to share this. Like, when each element comes into play.
Well, yeah, this reminded me, when you sent this, it reminded me of our little cheat, like our verification explanation thing, where we tried to do this, but not quite with ordering. Like, we just sort of grouped them as like
the
definitions.
sequence.
Yeah. Which we need to add. We need to add one here, which is n. Right, which is the order of the curve, not the prime.
Not the prime. Yeah. Usually your point, not the prime. Yeah, awesome.
So yeah, we'll throw that in there. Nice. Okay.
Oh yeah. No, that's it.
So now we can. Okay, so we should be able to plug these into, so it's a public key. We have a public key,
Mm-hmm.
and then we have signatures.
Yeah.
Right, and this fascinates me because the first thing you learn of just like the basic asymmetric cryptography is you provide a public key to the world, and then when you sign something, you can use the public key to verify the signature is correct. And now I know how that happens, at least in this example. So we could probably write a test, or maybe not a test. Yeah, we could write a test real quick.
It's so interesting that the public key is like 1 point in that curve.
Right.
This is me.
And that makes sense now too when you think about generating private keys, how they talk about entropy, right? So getting properly random, getting the proper amount of randomness in your private key generation is because if you're not truly random, if you just picked 1 as your number or whatever, that's easy to find. So you need proper,
to brute force, right?
to brute force. The commonly known private keys are just easy to find because they're the first ones you come across. But if you roll dice, for example, that's how I generated my private key, was I rolled a bunch of dice. And so that is
it's pure entropy.
Yeah, it's universal entropy. It's like dice that are, I don't know, maybe they're weighted a little bit, but I rolled them. I think the cold card recommends 256 times or something like that. It's just some absurd amount. All right, let's write some code. Do you have the live share? Are you join me? You are okay.
Mm-hmm.
Please aid me in this live share endeavor, because we need to write this test.
Okay.
We'll call it exercise 6, chapter 3, exercise 6. So we got our public key, because we're just going to use the words for it instead of the constants, and that's going to be a new point. If you want to start typing out these numbers, like the hash and the random X value
Mm-hmm.
and the signature value, I'm gonna.
I need to know how to do this in. I'll copy from your other
Oh yeah.
iteration.
Yeah.
Let's see. The one here.
It should be the, I was gonna say, make sure you take the 0x off the leading
Hmm.
0x, because we don't need it for the way we do things.
And it's a string, right? It's not an integer.
It's gonna be a string.
Big int?
Big
Not
U.
big int, not big U.
No, it'd be big U.
Big U.
Yeah, unsigned. U unsigned, because it's positive. Never negative.
But why do you have on the test above, you have big ints? I guess they end up working the same now.
Where do I have big ints?
Like on line 257.
257. Oh,
I guess, yeah, they just don't go negative.
Oh,
it works
yeah.
the same.
That was because, okay, so yeah, I was messing around earlier. I'll show you what happens when I put big U into here. It just maybe that was a mistake. Maybe it wasn't. I don't know. We'll see. There was a place earlier I had to use big ints because I was getting an issue with subtraction.
Mm-hmm. Oh.
Don't forget we gotta unwrap the big U int. Yep. And I'm just gonna number these 1, R1, Z1.
Nice.
And then we can just copy this. Actually, we don't actually need to do it. That's the beautiful thing about Rust is you can like reuse variable names and it just like overwrites it. So now we can just copy all of this. Put it down here. And copy. So I'm assuming one of these is not going to like work. If that makes sense? Like one of these signatures is not going to be valid for a given hash. And so
We'll see.
All right, so we need to. All right, we just talked about how we compare, how we do this. We take. We take all this math that we just did. Z R S, and we have the point. So we'll grab everything here down and copy it in underneath here, paste it in. Except this is not point, it's going to be public key.
Just a quick random comment, but it's just so nice to see Bitcoin sitting comfortably at 25K right now.
Yeah.
All the shit that went on last year.
Yeah. Yes, it is. I'm so I have like a running Excel spreadsheet that is tracking basically like where my break even point is, because I started buying like on the way down. Like I've never known a bull market. I've only known bear market, like number go down technology. And so I'm waiting. We're not there yet, but I'm waiting until we hit that point. And I just go to my wife and be like, hey, we just broke even.
Nice.
Everything from here on out is just pure profit.
I can say that I'm in a similar situation.
Yeah. And it's not even
Most
profit.
of-
It's
most
like,
of the school of 2021 is
yeah,
similar, right?
it's not even profit though. It's just like the more sats I accumulate, the more profit I have. Like I don't, it's not profit. It's just savings. I don't know. Like it's a weird thing, right? Because it's not, I don't see it as profiting because it's just dollars getting less valuable. I mean, I guess technically Bitcoin is getting more valuable in dollar terms, but I don't know. Dollar terms are so foreign to me now. Like I every time something's measured in dollars, I'm like, is it really worth that much though? Is it really?
So distorted.
Right. Okay. All right. We got this test. That was pretty quick. Nice. All right. Which one's going to break it? Oh, I guess they
Both passed.
both passed. I don't trust
not.
that, so I'm gonna. I want to check the answers in the back of the book. Don't trust verify. Chapter 3, exercise 6, and true. Okay, they're both true. All right, you win, Jimmy.
Okay.
Oh no. Cool. And so,
Should we call it for the night?
what time is it? 10 o'clock? Yeah, we can call it.
Yeah.
It's kind of getting excited, but I'm fine with calling it because we just did.
Keep going.
Well, we just did exercise 6, which is here. And we've got one more. The next thing we do, okay, so the next thing is we write a function for signature verification.
You feed the hash, the signature, and the private key, and it spits out if it's verified or not.
We create a signature class that houses the R and the S. So this would be a new thing here. Signature.
Oh, like a new file.
Yeah. Right? Because we're creating it, we're storing a R and S. So R, which is the random not value, random point X value. And this is, what is R? It's just a number, right? Yeah, because or no, it's a field element. Is it a field element? Yes, because it's a point.
Oh wow.
It's the
Yeah, and all points. Yeah.
yep.
Good point.
So it's a
Good
field
point.
element, and then S. What is S though? S is the
S is that equation is just a quotient.
yeah. I don't know what it
Like
is.
S equals.
Is it it's not the slope. I thought there was a name for it,
Yeah.
but it's a big. Is that
I don't think it's
is that,
S is like Z plus RE divided by K, but it's an integer. It's a
yeah, a big
I don't know if it's an
uint.
integer. It's
Yeah, and then it
a good
implements
question.
display, which see if we can do that.
Yeah, S is this. I'll just dump the equation here.
Right,
This is S. But
which takes in the
you're
hash.
verifying the signatures here. Yeah. The hash, the random number, the private key, and the random point and the random number. So interesting that it's used twice.
Yeah.
But you, when verifying, we don't need to know the equation. We just need the number.
Oh, that's what it is. See, this thing is. I forgot how to set up new files. Oh, I think. Okay, I think we're good. Yeah, we need to derive. That's what it is. Okay. We also forgot this. Oh, you know. Okay. All right. I know what's going on here. Here it is. Mod. Oops. Yeah, the mod file, the module file for SCP 256K1. We gotta add signature to it, and then we can address all these problems. Because we didn't import this. What? No, don't do that. What is this not like? It's only trait without a derived macro? What? Oh, it's not display, debug. Okay. And now we can write. Okay, so we'll be doing more with this class. Yeah, so it is going to be a whole file itself, which that's fine. And we can try to write the verify method using 256 point, which we go back to our point file, and I guess we need a verify method. Here's all the tests, so we'll implement it underneath here. Implement verify for point. No, I don't think that's. What am I doing here? So, okay, whoops. I'm way off on. We're not. Verify is not a trait. I'm thinking it's a trait. We need to go to the implement block of the point, and we implement it in here.
Mm-hmm.
Verify, and we take in self, I'm assuming, which means it's going to be called on itself. Oh, it's a lowercase self. And what are we returning? Oh, it's just a Boolean. Excuse me. Oh, there it is. I'm sorry. Oh, that's a class definition. Man, yeah, we're definitely gonna call it after this one, because now I'm getting off. and we get in Z, which is Z is just a big, the hash is just a big number, right?
Mm-hmm.
And a signature, which is going to be
is the tuple.
right, which is that signature class, which we didn't, or not class, but file rather,
Oh,
which
okay.
we didn't do. We didn't create a way to, like we don't have a way to create that right now.
Like the impl.
Yep. So we'll implement a new, and yeah, pass in R as a field element, and S as a big wint. And we'll return type self. And we just signature R is R and S is S. And that should work like that. Boom. Okay. And okay, so we have a way of creating our signatures now with the new method. And then we're just basically recreating the tests that we wrote earlier.
Mm-hmm.
So S inverted. I don't even know are you sure it's inverted? I don't know what
I
it
think
stands
so,
for.
yeah, because inverting an element is like multiplying by -1 or to the
Oh,
power
yeah,
of
yeah.
-1.
Yeah, you're right. So we'll go down here and grab these tests, all these tests that we wrote. Order -2. Because basically this function is just the test. Like we could just replace all the test code that we wrote with the function. Yep. Mod pow order -2 n. Except it's gonna be signature dot. Oh, which one? Oh, we don't have any getter methods for. We don't have any getter methods for it. Like we defined a way of creating a new one, but we didn't find a way of like getting it.
Mm-hmm.
Generate getter setter. Hey, look at that. That's nice. I love quick refactoring things like that. So now we've got it. Perfect. So signature dot S will get us that. N is not defined. Oh, where do we define N? Oh, we only defined N down in here.
Like the order in.
Yeah, but we want it available basically everywhere. So we could probably just create a function within this class. What? That's not right. Why is that not working? Oh. Because we did not do. Okay. Yep. All right. That makes sense. So the way Rust does its testing is you can like import things just into the tests themselves. So like these are all scoped into the test. And so what we did is we've imported some of these things into just the test. So we need to also import it into the main area. So now we have it. It's added. It's added in here.
Oh, cool.
Yeah. Okay, so verify. All right, cool. So we have that. We have n defined. Oh, self.n. Okay. So we need to call self.n because, all right, yeah, because n is on, in the implementation of this point, the SEC P256K1 point. So we're just referencing the type self to call n to make sure we're referencing like the right n that we're calling. And then, generator point, we also don't have, is also just defined down here in generator point. Where you at? Okay, here you are. So this is only defined in the test scope, the module.
Move it to...
Yeah, we're going to move it right next to n. Because now that we're using it in our actual implementation block, it's looking for it and it's not finding it. And again, we'll have to do a self : generator point because we moved it there. R, where do we get R? R's on the signature, right? Signature dot R, yes. We got problems here. What is this complaining about? Expected a field element found a struct. What is R giving us? Is a field element. Oh. Okay. Oh, that's not a field element because it's Oh, it would just be
the x coordinate of the random point.
Right, which is the field element, but we're multiplying. Okay, I think I know. Multiply by. Oh, that's not. What happened there? Hold on. Getting weird word wrap issues. So we have a field element, and we need to multiply the field element by. Didn't we have a way to? Oh, we get the number out of. Duh. That's what it is. Because the field element is a prime and a big wint. And we just need the number out of the field element. Because before when we were using R in our tests, we were just defining just a big wint. Like we're defining the X value of the number, not worrying about the field element of the point. If that makes sense. Which that makes me think we should probably we don't need a field element in this R number. Like we just need a big unit.
Yeah, because you're not gonna do field element math with this number, right?
No, I don't think so.
It's just, yeah.
I mean, we could. Well, we'll eat those words later if we're wrong,
Might, yeah.
and just refactor it. All right, verify. So we don't need to call get number on that anymore. All right, everything's good. It's all happy. The public key. Okay, so now we just need to do an equality check. Okay, all right, here. So we did the S inverted. We have U, we have V, we have total.
It's like one side of the equation, I think.
Which is U times generator point, which would be self generator point. There's probably a better way of defining that function so it's not like a weird self thing, but anyway, it's a problem for future pleb Lyra and Gary. Times self. What is self? Oh, times the point. Let's see if that math works. I don't think that math works. Oh, we needed to do. Remember, we created a function called multiply by. So it's just sort of the opposite of the way it's written. And then we would also do self. Oh. Multiply by v. And what is it complaining about here? Oh, we need to borrow it. Yep, mutably borrow it. Got it. This is just the rushed ownership thing. We just need to mutably borrow it because in our function we're mutating that. And cool. All right, and then the final thing is does total equals signature dot r. So one is a point. Oh,
Yeah, you see on the Python example, right?
Yeah. X dot number. Oh, it's a. So we're not expecting the point at infinity, so we can just unwrap that. It's probably a better way of handling that. But for right now, we're just gonna go with it. What? Expected structure found. Do we need to dereference it? Yeah, I guess so. Cool. So now we should be able to substitute this function into the test down below.
Mm-hmm.
And get the same like outcomes, right?
Mm-hmm.
So we can just start with this verify signatures thing. Oh yeah, we didn't make this public. We need to make it. Might not need to make it public, but well, yeah. We're gonna do that for right now. Why does that not work? Oh. Okay. I think we can define these functions outside of this implementation block, and they will work. And I say that with a question because I don't know. I don't know if they need to be functions since they're in this file. Or I don't know if they need to be public because they're in this file. We're going to need to update this and this. Dude, stop me if I'm like going too fast or something because I feel like I've just sort of gotten into a groove and I'm just doing the thing.
No, keep going.
Okay.
I'm not gonna absorb everything, but I'm definitely absorbing.
So yeah, with those functions, I just move them outside of the implementation block, so they're just part of this file, like part of this module, right? So when we define the module point, there are now functions in this whole module, which is basically the file, right? And then instead of saying self because they're not in the implementation, and then I think that will allow that should let us use them down here in. Yeah, like now we can just use them freely in our test because they're not tied to the implementation of a specific struct.
Okay.
Cool. And then, all right. And then we were going to just use the verify function here We don't need... We can just remove... Let's remove this. And you can just assert. Oh, we need a point to... Oh, we have a point. Perfect. Verify. And so we need to give it to Z. Which do we have as Z? Yes. Cool. And do we have a... we need to create the signature.
Mm.
And this is where we do signature, colon, new, where we give it an R value, which we already defined, and an S value, which we already defined. So we don't need, what is the use of move value? All right, so I don't think we need all of this crap in here anymore.
Mm.
Right, because this was the verification.
That's why you just coded
right
in the verify function.
Right, so we have the point. All right, let's run it, see what happens, because it should just work. Hey, cool. All right.
Nice.
Yeah. All right. That I'm happy enough with that. Like that worked, so I'm good. We can call it quits now because it is getting late.
So the signature, is it a function that's called the signature function in Rust? Or
No.
something else.
No.
Signature implementation or object or module.
So it's a struct is what it's called, or a structure, right? So in structures,
As in structure.
Structures have data types like fields in them. And you can actually define, you can actually say that this is like a public field on a struct, and then you don't need a getter or a setter. But we don't want to do that. We just, we probably could for this just because it's a very simple getter or setter. But by putting pub, it just means like you have unfettered access to just get and set this however. When it comes to like sort of like, it's called defensive programming in some regards, but you want to control how the thing is set or how the thing is get, right? So it's like you can store an underlying value, but you kind of control the flow of like, I don't know, if we wanted to check for null or if we wanted to check to make sure that we weren't getting 0 or something like that, right? Like we could put more checks in here to ensure that that was happening.
So then you access this struct to create the signature and then you input that signature into the verification algorithm along with the public key.
Right. Yeah, because the signature, according to the book,
the hash.
Yeah, the verify is taking this signature class or struct, in our case.
Then the hash and the point. Where does the point enter?
The point is defined, right? So this is defined on a point already. So you already have the point defined, and it is a verify function of the point struct, right? Because we did the implementation on verify inside the point. So we implemented verify.
So the point is the public key of the thing we're verifying.
Right.
And we're verifying the signature and the hash against that public key, against that point.
Right. Yep.
Nice. That's awesome.
So we're given a public key. That's a point on the curve.
Okay.
Yeah, and exactly what you said. Yeah. Nice.
And a signature hash.
Yep.
Then we can verify whether a signature is valid or not.
Yeah.
Awesome.
So the next is signing. We're going to create the opposite. We're going to create a signature from a private key. Yeah. So
And that's
cool.
where the entropy comes into play. I think he even mentions that you don't want to use like the Python random built-in
Oh
function
yeah,
because
yeah,
it's
yeah,
not random enough, right?
yeah, 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 yeah. The random K. So
Yeah, that's gotta be a good good random.
yeah. Well, Plevlier, thank you for sitting here and letting me sort of go into the zone there at the end. Um,
Yeah, no, that was great.
it's yeah. This is I felt like we overcame a couple of things here. Just some bonehead mistakes that we just kind of just like we're enlightened now. We know that the order of a curve is not the same as the order of a finite field. Whereas in a finite field, the order is a prime number, but on the curve, an elliptic curve, at least for the cryptography purposes, and we still might be all off on like our complete understanding of this, but um,
It is. They perform a similar role, so it's
right,
understandable that one
right,
would confuse the two.
right.
But now I think now we got it very clear. What's the order? What's the prime? The prime only affects the field elements and nothing else. All the rest is order all the way.
Yeah, yeah, yeah.
Yeah, we're getting places.
We're getting there. Cool, man. Well,
Yeah.
do you have any final thoughts before I stop
No,
the
I'm good,
recording?
man. This was great. This was a great session.
Yeah, I'm a little jazzed right now. Feeling bullish.
Yeah, 25K.
Just got to stay humble to stack sats though. DCA every
That's
day.
it. Yeah. Oh, no Lambo.
No,
Anytime soon.
no Lambo. We'll close it at that.